Yeah. So in this session, we will start with the timing parts in the combinational circuits. So first, we will see the timing parts in the combinational circuits, and we will go to the sequential circuits. So before we start the discussion about timing parts in combinational circuit, let me draw a combinational circuit which is involving some set of multiplexers and a logic gates. So let's say this is our black box. So today we will open our black box and see what are all the components are which are there in this black box. Let's say the circuit inside this black box is like this. So one OR gate which is connected here, and one NOT gate. So it is these are the inputs to my multiplexer, which is a 2 cross 1 multiplexer, 2 cross 1 mux, and this is my select line S naught, and this is one more mux, 2 cross 1 mux, and this is given to a buffer, and there is one more OR gate here which is given to this, and this output is given to one of the input of OR gate, and it is again divided like this, and this is given to P. So this is P, Q, R, and S, and this is S naught, and this is also 2 cross 1 mux, and this is our output which is given to output of the black box. So these are all my inputs. Okay, so these are all my inputs. So this is a circuit which is there in my black box. Okay, so we need to find at what time we are getting the output. So at what time we are getting the output. Okay, so for finding that at which time we are getting our at which particular time we are getting our output, we need to know the propagation delay and critical path, false path, all the terminologies we need to know. So that's why first our agenda is to learn these terminologies in combinational circuits, which are propagation delay, that is input to output delay, node delay or gate delay, input to intermediate path, and critical path and false path. So after learning this all these terminologies, we will be able to calculate the delay which is involved in this particular circuit. Okay, so we can estimate the delay, like how much delay we will get in this particular circuit. So is this agenda clear? Yeah, I hope this agenda is clear now.
Yes, it is.
Yeah. So
Yes.
basically these are the timing paths involved in combinational circuits. First, these are the delays. One is propagation delay, and second is node delay or gate delay. Next, we are going to learn about what is meant by critical path and false path. So after learning this, we will come back to this circuit again. Okay. Now, coming to the propagation delay. So propagation delay often denoted by TPD. So the propagation delay is denoted by this symbol TPD. So in our future sessions also, TPD means propagation delay time period. Okay, or simply TPD is a time interval between when an input signal is applied to a logic gate and when the output of the gate responds to that particular input. It is a time required for the input change to propagate through the gate and produce a corresponding change at the output. So this is the definition of propagation delay. Now let's see with a example. So let's see a NOT gate, simple NOT gate. So I hope you are familiar with this symbol of NOT gate. So this is the input and this is the output of our NOT gate. Okay. So if we apply, ideally speaking, if we apply anything at the input, let's say if we apply 0, then we will get output as 1. And if we apply 1, we will get output at 0. So at 0 nanoseconds, if we apply the input, so ideally speaking, at output, we will get the, so if we apply 1 at the output at 0 nanoseconds only, we will get the output as 0. So if we apply, wait a minute. So if we apply input at 2 nanoseconds, I am speaking about ideal case first. Okay, I am speaking ideal case. So at 2 nanoseconds, if we apply the input, let's say our input is 0, then at output at 2 nanoseconds only, we are getting the output as 1. Okay, so this is the ideal case what we have learned so far in digital circuits. Okay, So, but practically speaking, what happens is, but practically speaking, what happens is there will be a effect of delay which is called as propagation delay. Okay, there will be an effect of delay which is called as propagation delay, which will be involved in this output generation. What happens is, so let's say we are applying at t is equal to 0 nanoseconds. If we are applying the input, let's say 0, we are applying to this NOT gate. Okay, we are applying this input 0 to our NOT gate at t is equal to 0 nanoseconds. So ideally speaking, practically speaking, we will not get the output at t is equal to 0 nanoseconds. We will not get the output at t is equal to 0 nanoseconds. There will be some delay involved to get the output. There will be some delay involved to get the output. So this delay is called as propagation delay. This delay is called as propagation delay. Is it clear? Is it clear the difference between the ideal scenario and practical scenario? So at t is equal to 0 nanoseconds only, we will not get the output practically. We should wait. So there will be some delay involved to get the output of this logic gate. Is it clear?
Yes, yes.
Yeah. So let me show with a timing diagram. So let us say uh, this is our reference clock. This is at time t is equal to 0 nanoseconds, and let's say after some time period t is equal to 1, t is equal to 2, like this, our clock is there, and this is our input. So let's say I'm applying my input at time t is equal to 0 nanoseconds. Okay, so this is my input which I have applied, and I'm changing my input at time t is equal to 2 nanoseconds. I'm changing 1 to 0. So this input I'm feeding it to my NOT gate. This input I'm feeding it to my NOT gate, and I will be checking my output. So what will be my output in this case? So initially it will be unknown. So ideally speaking, I should get the output at t is equal to 0 nanoseconds when I apply the input. So this is the ideal case. This is the ideal case output. Okay. So what will be my output? It should be 0, and the input is changing from 1 to 0 at t is equal to 2 nanoseconds. So my output will change from 0 to 1 at t is equal to 2 nanoseconds only. This is my ideal case. Okay, now in case practically speaking, there will be some delay involved. So here initially the output is changing from 0 to 1. So there is a change in the input. Here there is a change in the input. So the change to be reflected at the output, it will take some delay which is called as propagation delay. Okay, so to reflect the change, it will take some delay which is called as propagation delay. If there is any change in the input, so to reflect the change in the output, to see that reflection to see the change in the output, there will be some delay which is called as propagation delay. Here in this you will understand clearly. So at t is equal to 2 nanoseconds, the input is changing from 1 to 0. So to see the change in the output, we need we will it will take some delay. So this is the delay. So this is a practical case. So you can see here it is taking some time to get reflected. So the input is changing from 1 to 0, but the output is taking some time to show the out. So the gate is taking some time to show the output. So this time is called propagation delay. Okay, is it clear? So this is a practical case, propagation delay. So this time period is called TPD, propagation delay. Okay. So now you can understand this definition clearly. So the propagation delay is a time interval between when an input signal is applied to a logic gate and when the output of the gate responds to that input. So after applying the input to a logic gate, the gate will take some time and it will respond to the particular input. So that is called the propagation delay. So it is a time required for the input change to propagate through the gate and produce a corresponding change at the output. Okay. So the propagation delay determines the speed at which a digital circuit can operate. So the sum of the propagation delay through a series of logic gates define the overall delay of a signal from one point in a circuit to another. For example, if we have a NOT gate here and a AND gate here, let's say this is our another input, this is also another input, and it is given to a buffer like this, and it will be given to a OR gate. So this is input. So let's say the propagation delay here TPD is equal to 3 nanoseconds, and propagation delay TPD is equal to 4 nanoseconds, and TPD is equal to 1 nanosecond, and TPD is equal to 2 nanoseconds. So here, let's say we will not apply any input here. Let's say it is grounded. Okay. Now, yeah. So at what time we will get the output in this case? After how many time period, how much time period our output is getting? So the input should flow through all these gates, NOT gate, AND gate, buffer, and OR gate, and it will reach the output. So this is a path. Okay. So this is called as a path. This is a combinational path. This is called as a combinational path. Okay. Because there is only all the combinational circuits involved, so it is called a combinational path. So the total time period taken by the input to reach from the input side to output side, which is calculated by TPD, is equal to TPD, which is equal to 3 nanoseconds plus 4 7 plus 1 8 plus 2 10 nanoseconds. It will take for the input to pass through all this combinational path. So this is how we calculate the propagation delay of this combinational path. Is it clear? So the propagation delay determines
Yes.
the speed at which a digital circuit can operate. So we can from this we can calculate, right? So from this propagation delay, if we get the propagation delay, we can get the frequency also. Frequency is nothing but 1 by propagation delay TPD. So we can get the frequency of operation. Okay. So like that we can get how much speed the a particular circuit is operating. So the sum of the propagation delays through a series of logic gates define the overall delay of a signal from one point to another in a circuit. Okay. Now, so the propagation delay can be broken down into two main components. One is rising propagation delay, and second one is falling propagation delay. Now let's see them. So coming to rising propagation delay, so the time it takes for the output to a change from a low logic level to a high logic level after the input changes. So for example, in our NOT gate example only, we can see rising propagation delay. This is our rising propagation delay. So if there is any change in the output from 1 to 0, so if there is any change in the input from 1 to 0, so to get reflected the change, so for showing the output, it is taking some time, right? So the output for changing from 0 to 1, it is taking some time. So this is called rising propagation delay. That is the output changing from 0 to 1, which is called as rising propagation delay. Let's say at this time interval, that is t is equal to 3 4 5. So at, let's say t is equal to 5 time unit, our output is again changing to, sorry, our input is again changing to 1. Okay. Like this, if it is changing, then again what happens, after some time delay, the output will change. After the input changing from 0 to 1, taking some time delay, the output will change. Let's say it will change here, okay, from 1 to 0. So this amount of time is called falling propagation delay. Okay, falling propagation delay. Is it clear? The rising propagation delay and falling propagation delay, is it clear? Rising means simply the output is changing from 0 to 1. Falling means the output is changing from 1 to 0. The delay which is taking is called propagation delay. Okay. So the So the time it takes for the output to change from a low logic level to a high logic level is called uh, to a high logic level after the input changes is called rising propagation delay. In that example we have seen, right? So that is called rising propagation delay. Now, similarly, falling propagation delay also we have seen in that example. So the time it takes for the output to change from a high logic level to a low logic level after the input changes. This is called falling propagation delay. Now, the total propagation delay is calculated from this rising and falling propagation delay. So the total propagation delay is given by rising propagation delay plus falling propagation delay. Falling propagation delay. Okay, so this is the propagation delay of this combinational circuit. So this is how we will find the propagation delay of this combination circuit. Is it clear?
Yes.
Yeah. Now let's see one more type of delay which is called as input to intermediate node path, or it is also called as node delay or gate delay. So in digital circuits, a node is a point in the circuit where the signals are routed between the different components or logic gates. So it could be a connection point between the output of one gate and the input of another gate, or it might involve more complex interconnections in a large integrated circuit. For example, if two gates are connected like this, let's take the example of this NOT gate only. So if two NOT gates are connected like this, so this point is called as a node. Okay, so this point is called as a node. So the delay involved by the signal at this particular node is called node delay, which is called as node delay. So this will also play a role in the overall delay. Okay, so the with the in addition to propagation delay of this particular logic gates, this node delay will also be playing a crucial role in the calculation of the time period. Okay, so this is the definition. Simple term. A node is a point in the circuit where the signals are routed between the different components or logic gates. So it could be a connection point between the outputs of one gate and inputs of another. Okay, so this is the node delay or gate delay. So node delay is the time it takes for a signal to propagate through a node in the circuit. So this delay is influenced by various factors related to physical and electrical characteristics of the node. Okay. So the factors contributing to the node delay are resistive path. So there may be a resistance in the path, or it may be also dependent on the materials and dimensions of the wire or the circuit path which is designed. So these are all the factors which are affecting the node delay. And it may be also multiple loads. So if a node drives multiple gates or components, high fan out, so the combined capacitive load increases, leading to greater delay. So these are all the factors which are influencing the node delay. Okay, so is it clear? Yeah.
Yes.
Now let's discuss about this topic which is called as critical path. So the critical path in a digital circuit is the longest path that a signal must travel from the input to the output, considering all the logic gates, interconnections, and timing delays involved. It is a crucial concept in timing analysis and circuit design because the critical path determines the maximum speed at which a circuit can operate. So this is the definition of the critical path. We will understand this critical path uh, by using the example which I have shown in the first slide. So for now, understand this critical path is the longest path. Critical path is the longest path. For example, let's take a scenario. If you are starting from point A and you have to reach to point C. Okay. So from point A to point C, for reaching, you will go to point B, and from point B you will go to point C, or there is one road from point D to point C. Okay. So in this path, if you have, let's say, more traffic jam and more number of signals, and in this path you have only signals but no traffic jam. Okay, so which path will be the longest path? So the path which you are waiting for more time, you feel like it is the longest path because you are taking more time, right? You are taking more time because of this you will feel that this is the longest path, but it is not the longest path in a sense, but it will feel like it is the longest path. And if there is no, if there is less traffic jam and only some signals, and if the signals also are green every time, you will reach the destination faster. So it will feel like it is the shortest path because it is taking less time. Is it clear? Is my example, is it clear?
Yes, yes.
Yeah. So this is what we are going to do. So we are going to find the critical path, which is the longest path, and we are going to find the shortest path. So the shortest path is the route taken by a signal through the circuit that experiences the least amount of delay. Okay. So the route taken by the signal which is experiencing, remember this term, which is experiencing least amount of delay. So which is experiencing least amount of delay, it is called as a shortest path. So this path is crucial for the applications where the speed is prioritized, as it is directly influences the response of the circuit. Now, so now we are going to see this shortest path, critical path. I hope this definition of critical path and the shortest path is it clear. Yeah. I hope the example of this critical path and the shortest path is clear. Now, let's see the definition for this false path. So, a false path is a timing path in a circuit that can never be activated or exercised during the normal operation. So, this means that even though a signal can propagate through this path logically, it will not do so in the practice due to a specific condition in the circuit operation. This definition, if you see, you cannot understand. We will see the practical example of this false path. Okay. Yeah. So now let's see the critical path, false path, and shortest path by taking the example which I have shown in the first slide. Yeah, this is the circuit which I have shown. Okay. Now, so let's say this is our, these are all our inputs, and this is our output. Okay. Wait a minute. Let me add some more slides here. Okay. So what are all the paths available for this input to propagate and reach the output? So can you help me with this? So there is first path, path 1, which is input, input to OR gate, OR gate to 2 cross 1 mux, and we are reaching to output. So this is our path 1. Okay. So this is our path 1. Now, coming to path 2, which is input, input to, input to OR gate, OR gate to, we are going to multiplexer, multiplexer to, we are going to this is one more path, or input to OR gate, OR gate to multiplexer, multiplexer to OR gate, OR gate to multiplexer, OR gate, OR gate to multiplexer, multiplexer to output. So this is one more path. Okay. So what is this? OR gate, multiplexer, OR gate, multiplexer, and output. Next, what is another path? Input to NOT gate, NOT gate to multiplexer, multiplexer to this one, multiplexer. Okay, so path 3, uh, we have one more path also in this, OR gate to multiplexer, multiplexer to multiplexer. Okay, OR gate to multiplexer, multiplexer to multiplexer to output. Okay, path 4, path 4 is uh, input to NOT gate to mux, mux to OR gate, and mux. Okay, is it clear how I am writing this path? Is it clear? So NOT gate to NOT gate to multiplexer, multiplexer to output. And one more path, which is path 5, which is input to buffer, buffer to multiplexer and output. Input to buffer, buffer to mux, and output. Okay. So from this, can you guess what is the longest path? Any guesses? So I will write it again. So path 1 is not plus mux, and part 2 is not plus mux plus not again plus mux, and path 3 is not mux mux, and path 4 is my not mux not mux. Okay, and path 5 is not mux mux. Okay, so these are all the possible paths. Okay, now can you guess what is the in which case can we get maximum delay? What is the longest path or the critical path, or what is the shortest path? Any wild guesses?
Path 2 and path 4 are longest path, remaining are shortest path.
Okay, so by seeing this, we can while guess that part 2 is critical part, right? Critical path. Okay, this is a wild guess. Okay, this one and this one are critical paths. Okay, critical path means longest path. That is, we are expecting that there will be more delay in this particular paths. Okay, is it clear?
Yes.
Yeah. So let us define some delays respect to this. Yeah. So let's say OR gate has a delay of. I'll write it here. Let's say OR gate has a delay of 2 nanoseconds. OR gate, let's say 4 nanoseconds, and MUX has a propagation delay of 3 nanoseconds. Okay, so what is the overall delay in this path 1, which is 7 nanoseconds? Okay, so the delay we are getting in P1 is 7 nanoseconds. Now, NOT gate is 4, right, and MUX is 3. So the total delay in path 2 is 4 plus 3 is 7, 10. 7 plus 4 is 11. 11 plus 3, 14. 14 nanoseconds in path 2. Okay. And here 4 plus 3 is 7. 7 plus 3, 10. 10 nanoseconds. Okay. And in path 4, 4 plus 3 7 plus 4 11 plus 3 14, right? This is the delay I'm getting. Not, yeah, what is the delay I'm getting? 14 now. So this is the delay which I'm getting, right? So while guessing, what I'm thinking is uh, path 2 and part 4 are my critical paths. Okay. Now let's see uh, false path. So we have seen the definition of false path, but now let's see it practically. So in our circuit, there is a select line, right? So this is our select line T. Okay. So this is a select line for our two multiplexers. So we will take the first case, that is T is equal to 0. This is our first case. T is equal to 0. Now let's see what happens if T is equal to 0. Here, if T is equal to 0, this is 0, this is 1, 0. So here our S naught will be 0, our S naught will be 0, and sorry, this is not buffer, this is not gate. Okay, this is not gate. So if T is equal to 0, what happens? Here this line will be selected. So what is the path here? This is a path, right? This will be our output, and if T is equal to 0, it will be 1. So this will be selected, right? Is it clear? OR gate, multiplexer, multiplexer. If T is equal to 0. Are you getting right? What I'm explaining, is it clear? So if T is equal to 0, the path will be input, input to OR gate to multiplexer, multiplexer to multiplexer to output. Okay. Here, if T is equal to 0, this will be selected. This input will be selected. So OR gate to multiplexer, multiplexer to. So if T is equal to 0, it will be 1 here. So it will be given, and this will be selected. So OR gate, multiplexer, multiplexer to output. This is the case. What is the delay here? What is the delay we will get here? It is 4 plus 3 7 plus 3 10 nanoseconds. Okay. If T is equal to 1, what is the scenario if T is equal to 1? What happens if T is equal to 1? Then this path will be selected. Not gate to multiplexer, multiplexer to output, and T is equal to 1. So this will be equal to 0. So this path will be selected. So from S to NOT gate to multiplexer to OR gate to multiplexer to output. Okay. I hope the path is clear. So what happens here? T is equal to 1, input to NOT gate to multiplexer, multiplexer to OR gate. Okay. Is it clear? So what happens? I think
Yes.
I haven't specified the delay for OR gate. Oh, sorry. OR gate 4 nanoseconds. Oh shit. Okay. So okay, OR gate 4 nanoseconds and NOT gate, let's say it is 1 nanoseconds. Okay. So here it will be 1 plus 3 4 nanoseconds. Sorry. For OR gate it is 4 nanoseconds, and NOT gate it is 1 nanoseconds. Okay. So here NOT gate it is 1 nanoseconds and OR gate 4 nanoseconds. Okay. So it will be 1 plus 3 4, 4 plus 1 5, 5 plus 3 8. Anyways. Okay. Actually, I've done something wrong. Nothing. Just here, instead of calculating this OR gate delay, instead of calculating this NOT gate delay, I've kept OR gate delay. That's it. Okay. So no problem in that. Just a value changes. That's all. Okay. So I hope the concept is clear. Now, if t is equal to 1, what is the path? Input to NOT gate and NOT gate to multiplexer. So NOT gate propagation delay is 1 nanosecond plus multiplexer delay is 3 nanoseconds. That is 4 nanoseconds. Is it clear?
Yes, sir.
Yeah. Now, so if t is equal to 0, this is the path we are getting. So this is the path we are getting, and if t is equal to 1, this is the path we are getting, right? So wait a minute. Yeah. So this is how we will actually calculate the critical path, and I think I have taken the values wrong, so that's why I was not able to conclude this point. So yeah. So is it clear how to calculate the critical path? Is it clear?
Yes, sir.
So for getting the false path, actually I have taken the first scenario wrongly, so that's why we are getting wrong. So let me modify that. So path one is not plus mux. Here not is 1 nanosecond and mux is 3 nanoseconds, which is 4 nanoseconds. And is part 2 is not plus mux plus not plus mux. Previously, I took OR gate delay. That's why it was not 3, 1, 3, 4, 5, 8. Okay, and sorry, this is not. This is OR. This is 4, 4. Okay, 4 plus 3 7 plus 4 11 plus 3 14. Okay, and path 3, which is OR mux. I'm not taking any values of t. Okay, so which is 4 plus 3 7 plus 3 10. And path 4, previously I have written wrongly. In case of or I have written not. That's it. Not plus mux plus or plus mux. So which is 1 plus 3 plus 4 plus 3, which is 11 nanoseconds. And path 5, which is not mux, which is 1 plus 3 plus 3, which is 7 nanoseconds. So this is the case which we have seen without considering the select line inputs, right? So in that, what we are getting the critical path, that is 11 nanoseconds, right? This is 11 nanoseconds. This is a critical path we are getting. Is it clear? Sorry, I think 14
Yes.
nanoseconds. 4 plus 4, 8. Yeah. So this is the critical path we are getting, path 2. But after considering the select lines, what we are getting, what is the longest path we are getting? 10 nanoseconds. You can see the difference here. Can you see the difference? So after considering the select line, we can see that this path is not getting selected at all. Or plus mux plus or plus or. Is it clear? I will show that path. So this is basically a false path. What happening is this path is not at all getting selected. Or plus multiplexer plus or plus multiplexer. Okay, this path or plus multiplexer plus OR plus multiplexer plus output. Is it clear? That is when t is equal to 0, what is happening? This OR path is getting selected. So input to OR gate to multiplexer, and since t is equal to 0, here the NOT gate is present, so it will be 1. So select line is 1. So this path will be selected. So this OR gate is not at all involved when t is equal to 0. So that's why this path OR plus multiplexer plus OR plus multiplexer is not at all getting selected. But when we are calculating without considering the select lines, we are getting that path is the longest path or critical path. That is 14 nanoseconds we are getting. So we are making it as the critical path, but it is actually a false path. That is, that part is not at all getting executed. Okay, the signal is not flowing at all in that path. Is it clear?
Yes.
So this is how we should be careful while calculating the critical path and the false path. Okay. So initially what mistake I have done is, instead of OR gate I have written the NOT gate, so that's where I got confused. So yeah, that is a small mistake I have done. So instead of OR gate I have written NOT gate. That's it. Here I have modified it. Okay. So I hope the critical path and the false path and the propagation delay and the node delay, all this is clear. So yeah, so if you are having any doubt, you can ask me. Thank you. So that's all for today's session. Thank you.
Thank you.
Yeah.